Okay, let's continue on where we left off. We're going to talk about speculation to parallelize single-threaded programs. That's part of the speculation lecture. And then we're going to focus on speculation to improve the performance of parallel programs. Now, this is a topic that has fascinated many people, and there are many readings that I can recommend over here. And these are some of the reference readings, and all of them are required. Well, that's a joke. The more you read, the better, of course. It's always good to read and understand the ideas and evaluate the different trade-offs between the ideas. This could give you a lot of good project ideas, and this could actually enable you to do great research as well. So I would actually recommend reading all of these papers. But some of these will be required, as I've already told you earlier, and as we will put up on the website. But I'll try to cover some of these. These are the reference readings over here. But there are many, many other readings that we can talk about. So the basic idea of taking a single-threaded program and parallelizing it on multiple hardware contexts is called thread-level speculation. This is also called speculative multithreading. And there are many examples of it. One example is dynamic multithreading, which basically I have briefly discussed. And I will give this reference over here. But that's an example of it. Akari and Driscoll wrote a paper in Micro 1998 about a dynamic multithreading processor. This is one example of speculation which we will not cover in detail, but I wrote it over there because it's an interesting approach also. The basic idea is whenever a thread gets to a function call, launch the function call on a separate hardware context. So core 0 executes the regular thread, core 1 executes the function call now, and core 0 doesn't twiddle its thumb at that time. Basically, it continues executing from the return point of the function call. So if you think about code, you have some code here and you have a call here. Basically, this call takes you to some function block, and this function block gets executed over here, and this the next instruction that comes after the call, let's say it's an add, the next block gets executed on this core 0. Right. This is basically function level speculation. At that function, you start a thread. And if there's another function within here, you start another thread, right? If there's another function, you start another thread on a separate hardware context. So that's how you dynamically multi-thread the program at the function level. Now, what happened, what they did over here was, if some of the values were not available, for example, were predicted to be produced by this function, they basically predicted the values. And actually, they predicted the value of the return value of the function. Return register value, right? Because function usually produces a register value that's returned. And if that's the case, then that register value is predicted, and this return point is executed with that predicted value. At the end of this function generates some results. And it also generates the register value. That register value is compared to this predicted value. And the result, if the prediction was correct, then the execution here was correct, right? If assuming that all of the predicted values were correctly predicted, right? All of the values that were produced by the earlier part of the program that must have been executed before the return point were correctly produced. So there needs to be some checking to ensure that that happened. And eventually the results get merged, and you merge the results using something called thread result buffers. And I'm not going to go through that in detail. This is a more complicated part of the mechanism. But that's they were able to parallelize programs at the function level this way. This is one example. The other way that this particular paper parallelized the programs was with loop iterations. So if you have a for loop, for example, what you can do is when you get to the beginning of the iteration, you can launch the next iteration in another processor. So basically, you can speculatively say iteration 0 goes here, iteration 1 goes here, core 0, core 1, iteration 2 goes here, core 2, and iteration 3 goes here, core 3. As many cores as you would like. And this is another form of speculative parallelization, right? Basically, you can actually predict the inputs to the iteration potentially also, even if there are dependencies between iterations. And you, of course, need to do everything else I said earlier. You need to ensure that the data dependencies, true data dependencies, are correctly satisfied and the iterations execute correctly. And if there's a dependence violation, iterations are actually iterations and subsequent iterations that saw the dependence violation are actually squashed. So this is the idea of speculative multithreading, thread level speculation. And people have especially looked at multithreading when you get to a function call, and multithreading when you get to an iteration. Basically, in a loop, you can try to parallelize the different iterations of the loop speculatively. And we will get back to these concepts over and over in this lecture. But the basic idea I've already given you, right? Divide a single instruction stream speculatively into multiple threads at compile time or runtime, right? And the key is speculatively. And you can execute speculative threads in multiple hardware contexts, as I've shown over here. And eventually, you need to merge the results into a single stream. For example, this function call needs to merge its results into the single stream such that the results appear as if you've executed that single instruction stream sequentially, right? That's the key idea. And of course, hardware and software, sometimes cooperatively, need to check if any true dependencies are violated during the speculative execution, and it ensures the sequential semantics. Because remember, we have sequential semantics in the single-threaded program, and we need to ensure that semantics. We're only under the hood parallelizing that single-threaded program by utilizing the multiple hardware contexts that are present in hardware. So one potential way of actually doing this is threads can be assumed to be independent. For example, here, the function call is executing another thread, and the return point of the function is executing another thread. Let's assume that they're independent. You can actually use value and branch prediction to break the dependencies between threads. In this case, the return value of the function can be predicted such that the code after the return point can be executed, assuming that it's independent, right? You don't need to wait for that data value. Waiting for that data value could be another option, but that reduces the parallelism between the threads, right? If it's predictable, it may be much better to predict that value that this thread needs to continue execution. Right? So basically, you can use value prediction to break dependencies between threads, and similarly, you can use branch prediction too. Of course, you need to verify such predictions in the end, because remember, this is a single instruction stream that we're speculatively parallelizing. And you can actually verify these predictions by executing a safe version somehow, right? Maybe you always execute the safe version, and also by checking some invariants, right? And we'll see one of those approaches, and you can think of other approaches. So one of the earlier works in thread level speculation was actually done here at Carnegie Mellon. This is Greg Steffan's paper, A Scalable Approach to Thread Level Speculation from Todd Murray's group. And this shows an example over here. Basically, I will go over this example on the slide. This is a hard to parallelize loop, if you would like. You have a while loop. Let's assume that this while loop executes many times. Basically, you have two accesses. One access loads from a hash table using one index, and the other access actually writes to this hash table somehow some value that's produced. Now, if you would like to parallelize this program, while loop, as a programmer, you have no idea if one loop iteration 1, is independent of the other loop iteration, right? It may be such that the first iteration is writing to an index that the next iteration is reading, or first iteration is writing to an index that 25th iteration is reading, right? But you have no idea because these indices are dependent on the data values input to the program, and as a result, as a programmer, it's very difficult to parallelize this program by breaking the loop iterations to be executed as on different cores, different threads, right? So, but using thread level speculation, what might happen is, basically, the idea is to speculatively execute consecutive iterations in consecutive processors. So processor 1 executes iteration 1 over here, right? This is called epoch 1, let's say. Processor 2 executes epoch 2. This is the second iteration. Processor 3 starts executing epoch 3. Processor 4 starts executing epoch 4, right? And these all execute dynamically in parallel, and basically these dependencies are kept track of, right? For example, processor 1 reads from hash 3, but that's okay, no other processor has written into index 3. Processor 2 reads from 19, processor 3 reads from 33, processor 4 reads from 10. So the fourth iteration reads from index value 10. And it turns out the first iteration actually writes to index value 10. So this dependence needs to be detected somehow. So this fourth iteration cannot execute in parallel with the first iteration, really, right? Because there is a dependence over here on the fourth iteration actually should get the correct value, whereas it may execute and get the wrong value. Because here, if you look at this in time, it got the fourth iteration's hash 10 read executed earlier than first iteration's hash 10 store, right? Store to index 10, index 2, which is 10. So in this case, this violation needs to be detected because in the sequential order of execution of this while loop, the first iteration should execute before the fourth iteration. So that's the idea in thread level speculation. How do you actually detect this violation? And the idea is to use the coherence protocol to detect this violation. We'll get back to this. But assume that there is no violation. Assume that dynamically these values turned out such that no thread wrote to an index that a later thread actually read. In that case, all of these threads attempt commit at the end of their iteration. And in this attempt commit function, basically they check if there was a violation. If there is no violation at all, a violation meaning the data value read by this thread was actually written by some other thread, and this thread actually got the wrong value because it executed speculatively earlier, right? If there is no violation, then these threads can commit, right? And this commit needs to be in serial order actually, because you need to preserve the sequential semantics of the program. Remember, this is a serial program again. And these threads actually commit in the serial order. And the thread commits assuming the previous thread has committed and it has no violation, right? Well, if there is a violation that needs to be detected, and that gets detected with the coherence protocol, when this processor actually reads hash 10, it doesn't know someone else has written, but when this processor later writes to this index 10, this memory address with index 10, it basically sends an invalidation request to this processor, and this processor, if it has read, remember the principle, when you do a speculative read, you mark the cache or some location saying that, oh, I've actually speculatively read this value. And if later an invalidation comes from an earlier epoch, earlier processor, well, epoch is the right thing in this case because processors can execute later iterations also. An earlier epoch actually writes to a location that was speculatively read by a later epoch, and you can determine this through the coherence protocol. The coherence message protocol sends an invalidation message to that address, and this cache receives that invalidation message and checks if that block is actually speculatively read. If the block is actually speculatively read, which is the case in this case, and if you're receiving an invalidation from an earlier epoch, that means that you read a value speculatively earlier than someone else should have written to it. As a result, this is a data dependence violation. You read the wrong value. Once you read the wrong value, now you need to squash this thread, this epoch over here. And this shows how that actually happens over here. So I'm going to go over this slide again in this. Basically, this is processor 1 and processor 2. Let's say you have epoch 5 and epoch 6 executing, and epoch 6 is the earlier epoch over here. Epoch 5 is the earlier epoch. It's earlier in the logical sequential order. Epoch 6 executes speculatively. It basically does a load from this memory location, and once it does the load, it needs to send a read request, and it gets the data cache block in its cache. And there are two values, 2 bits added to each cache block saying whether or not this cache block is speculatively loaded and whether or not this cache block is speculatively modified, as we've discussed earlier, right? When we talked about stores and loads and memory communication earlier. Basically, when this processor does the load, this speculatively loaded bit is set to 1, right? And it's set to 1, and later, let's say, and this processor continues executing with the value of the load. It gets the value of the load, but it's speculative. It may be not the correct value. And later, this epoch 5 executes on processor 1, and it basically does a store to the same to what happens to be the same location, right? Q and P are the same, basically. But these are pointers, so you do not know the location statically, so you cannot parallelize this program. Basically, this does a store. It changes the value from 1 to 2. In this case, the value was set to 1 over here with the load over here. It changes the value from 1 to 2. It basically sets a speculative modified bit in its cache, but it's not important here. That's for other purposes. And it basically, because it's doing a store, it needs to send an invalidation message, right, to everybody else. Remember, this is a cache coherent shared memory machine. When you're doing a store to a cache, it's an invalidation-based protocol in this case. It basically sends an invalidation message to all of the other processors that have the location, either through a directory protocol or through a Snoopy protocol, right? This invalidation message reaches the L1 cache of this processor, which is executing epoch 6. And the invalidation message also contains information about which epoch is invalidating. So it has this epoch 5 tag attached to it. And when the L1 cache gets this message, it checks, oh, this invalidation is coming to a speculatively loaded block, which has this bit set. And it's coming from an earlier epoch, logically earlier epoch than the epoch that I have, which means that I've speculatively loaded potentially the incorrect value, right? And in this case, basically, you detect that this is a violation. Once this invalidation message is received, you know that you've read the wrong value and the violation is detected. So there's a violation signal that's set to true over here. Now at this point you can start squashing everything actually, but in this paper they don't do that. What they do is they wait until this attempt commit time, and this attempt commit time actually checks whether the violation bit is set in the cache, and if that violation bit is set, then it starts the recovery process. But it basically flushes this entire, squashes this entire epoch over here and squashes all of the other epochs that come after it. So this is how you can use cache coherence to detect a read after write dependence violation through the invalidation messages. Now if this was an update based protocol, you could do the same thing, right? You could actually be even smarter if this is an update based protocol. If this is an update based protocol, this epoch would send a message with an update request to this location with its epoch ID and the data, and you would still know that this is speculatively loaded, and you can actually say if the data value that you loaded doesn't match the data value that's sent, then you've gotten the wrong value, right? Then there's a violation. If the data values actually happen to match, then you've gotten the correct value by chance, potentially. Because there are actually a lot of stores that are silent, right? These are called silent stores. And Kevin Lipak has a paper in Micro 2001 on the silent stores, and I'd encourage you to read that paper. Basically, this means that store is storing the same value to the location, same value as the location had before. So an update-based protocol can have that optimization, and it can check whether the data value has changed or not, instead of checking only whether the address is going to be modified with some value that's not known. Okay? So that's the idea. This is how you can detect conflicts in thread level speculation by leveraging the underlying coherence protocol. This paper actually presented some results, and I'll briefly go over them. I'll encourage you to read this paper. There are actually some promising results. These are some applications, and this is on a 4-processor single chip multiprocessor, 4-processor single core multi-core machine. And you can see the speed ups. There's the parallel region is over here, and the speed up that you obtain in the parallel region, this is just the parallel coverage. So if you see that the coverage of the parallel region is not very high, which means that Amdahl's law limits the speed ups to begin with over here. But these show the results. For example, in some applications you get significant performance benefit with 4 processors, up to 46% performance benefits, and the performance benefit keeps increasing as you add more processors. And remember, this is purely done with thread level speculation. This is a single threaded application, parallelized. On some applications, for example the JPEG compression, you get less benefit, only 8% on the overall program and 94% on the parallel region. And you can see the speed up curves as you increase the number of processors over here. This is the single threaded version, up to 8 processors. And this is the execution time of the region, which is the parallel region of the program that they parallelized in this work. So if you can see that this application actually scales in the parallel region, but there are cases where, for example here, the performance increases up to 4 threads, but as you go up to 6 threads and 8 threads, performance starts decreasing. Execution time starts increasing. In fact, the execution time with 8 threads is worse than the execution time with 1 thread. Why would this happen? Well, this could happen due to multiple reasons, right? Actually, there are many reasons, but in this case, there are lots of dependencies between threads, so there are lots of squashes. That's one reason. There's a lot of ping-ponging that starts happening because now the data gets distributed across the private cache, and then you get a lot of invalidations because of the dependencies. And there's bandwidth contention that also happens. These are basically due to the problems that we've discussed in the bottlenecks in the parallel region, right? And these are actually discussed in the paper. I'd encourage you to read this paper. But thread level speculation approaches like this are quite promising. The downside, as you can see, the upside is you can get significant speed up in the parallel region. The downside is some speed ups are actually low and the complexity may be high in the system. So I'd encourage you to think about the advantages and disadvantages. Okay, let's move to another seminal paper. This is actually an even earlier paper that discussed thread level speculation. This is called Multiscalar Processors. And the key idea is to exploit implicit thread level parallelism within a serial program, just like what we've discussed earlier. But the approach is different here. In this case, the compiler divides programs into tasks, and the tasks can be defined unclearly, but we will discuss this. And these tasks are basically the portions of a single-threaded program. If you think of single-threaded program as executing a series of instructions that are dynamic, that are composed of static blocks of instructions, basically tasks are some arbitrary subsetting of those blocks. So let's say this is your program, and these are some blocks of instructions. Your tasks are basically blocks in your program, right? Task 0, task 1, task 2, task 3, task 4. They could be loop iterations. They could be functions, right? But the key thing is this is a sequential execution over here. Okay? And we'll see an example of this. Tasks are scheduled on independent processing resources. Instead of executing them on the same processing resource, thread 0 goes to one processor, thread 1 goes to another, thread 2 goes to another, ... Right? Very, very similar to before. And hardware handles register dependencies between tasks. Because these are coming from the same program, there could be register dependencies. This could be writing to register 2, this could be reading from register 2, right? And there may be many dependencies. Hardware handles this register dependencies, but compiler specifies which registers should be communicated between the tasks, because compiler knows that information, right? Remember, register dependencies are known to the compiler. Compiler, when it creates the tasks, it basically says, oh, these are the registers that I need, and these are the registers that I'm actually likely to produce. I can produce. Right? And this information is conveyed to the hardware such that the hardware can communicate between the threads. And we will see an example of this. And memory dependencies are handled through memory speculation. Basically, hardware detects and resolves the misspeculation between the tasks, and through something called an address resolution buffer that we will discuss. So this, I would recommend actually both papers over here, but the required paper is a Sohi paper, Multiscalar Processors, that appeared in ISCA 1995. This is an earlier paper, the expandable split window paradigm for exploiting fine-grained parallelism. A lot of the concepts are not mature enough yet, but it was also published in ISCA 1992. And certainly the name multiscalar is more catchy, right? Expandable split window paradigm for exploiting fine-grained parallelism doesn't sound that catchy. But when you say multiscalar, it starts becoming more catchy. Anyway, that's the joke of it. But basically, this figure from the multiscalar paper clearly describes what they're trying to do. If you want to have a single-threaded program, and if you want to execute operations in parallel, you would like to execute instructions one by one and figure out, have a large window or execution, right? To actually improve the performance of the program, right? Out of order improves the performance of the program by looking at a large window of instructions. And we already discussed why that large window was harder to build, right? And that led to the multi-core. Increasing performance by building large instruction windows is difficult. Now, if you have a large window of instructions, and if you want to execute multiple instructions per cycle, one of the limitations is, for example, if you want to execute 100 instructions per cycle, let's say, you want to extract that kind of parallelism from your program. To be able to do that, you need to look beyond many instructions in the instruction stream, and also you need to have a width of 100 instructions per cycle, and also you need to have a register file that can support the execution of 100 instructions per cycle, which means that you need to have 200 ports, right? Assuming each instruction has 2 input values, 2 source registers. So building this multi-port register file is tough, right? And this was one of the reasons for a move to multi-core. Remember the Kunli-Olukutun paper in 1996 that discussed a multi-ported register file as a part of the technology push of what makes single-core, single-threaded processors unattractive. a similar reason happens here in 1992. And basically, 200 port register file is not scalable. So why don't we actually, instead of having a huge large window, why don't we chop up this instruction window and execute the different pieces in parallel in different processors. Processor 0 executes task 0, processor 1 executes task 1, processor 2 executes task 2, and processor 3 executes task 3. Now each processor looks at a smaller window, but you can process the entire window, maybe a similar size window, in parallel. And the added benefit is each processor has a simpler register file, right? Why? Because now in order to get the same bandwidth, let's say you want to do 100 instructions per cycle. I was very aggressive here. Now you can do only 25 instructions per cycle in each of these processors, which means that you only need 80 ports. And of course, if you scale this to reasonable values, if you say I want to do 16 instructions per cycle total, you need 32 ports here. Building a 32-port register file is still pretty tough. But if you want to execute 16 instructions, you just need to execute 4 instructions per cycle if you have 4 processors, which means that you need to have only 8 ports per register file. And that's actually much more palatable, right? So that's the idea, basically. Now you have a distributed register file and smaller windows, and you split the large window into smaller windows, and you're extracting parallelism through the multiple hardware contexts. Right? And you have this distributed register file, but you need to somehow ensure that the communication happens correctly in the register file. And we'll take a look at how multiscalar does that. I've already given you the basic idea. So the key idea, exploit parallelism that is provided by a large instruction window in a sequential instruction stream by chopping up that large instruction window into smaller tasks, smaller windows, and executing tasks on those windows in parallel. This not only improves the parallelism, hopefully, because you don't need to extract it from the sequential instruction stream through out-of-order execution methods that are less scalable, for example, through the reservation stations. Hopefully you can extract parallelism much more easily if you create the tasks nicely and assign them to different processors. And also this hopefully simplifies the hardware because you don't need to build these less scalable structures like large reservation stations, large multi-ported register files, because they are now distributed. Reservation stations are distributed over here. Multi-ported register files are also distributed, and you have fewer ports in each. So that's the benefit. And this is the model of execution. Model of execution is very similar, as I've said here. With the superscalar processor, you have a single centralized window, and you have a single program counter, and this is a dynamic instruction stream. With multiscalar processor, you have multiple distributed windows. You basically have multiple program counters. You have program counter 0, program counter 1, ... over here. And there's a task selection, task assigner over here that assigns different tasks to different cores. So you need to have that centralized engine that actually assigns which task should go to which core. Okay? So what is a task? We've been talking about task. Basically, a task is a subgraph of the control flow graph. It could be a basic block. It could be multiple basic blocks. It could be a loop body. It could be a function. Basically, it could be a loop iteration, right? Tasks are selected by the compiler and conveyed to the hardware, and tasks are predicted and scheduled by the processor. And tasks may have data and or control dependencies, and they need to be resolved. And this is how a multiscalar processor actually looks like. Basically, it has this task sequencer that sequences through the tasks, figures out the next dynamic task, and assigns it to the next processor that's available. And these processors or tasks are ordered in a logical order, in the sequential order that they were assigned. The head task is the oldest task in the system that's executing on this processor, and tasks are actually ordered in a round-robin fashion. This is the next oldest, and this is the tail task, which is the last task over here. And register files are connected through a ring. Basically, when this task actually produces a data value that may be needed for a later task, it basically sends the data value across this ring, and that the tasks that need that data value basically capture them and place them into the register file. Now this is how the full empty bits, remember the full empty bits in the register file, get set. Basically an earlier task sends a produced value, and the consumer task captures the consumed value from the ring and basically sets the full bit or ready bit of its register, of the register that it's waiting. And how does it know to wait for the register? Well, the compiler specifies that, oh, this register is actually going to be produced by some other task that's earlier than you, because the compiler can analyze those dependencies, right? Okay, so there are several things that the compiler needs to do in multiscalar. First is task selection. You need to partition the control flow graph of a program into tasks. And there are many things that go into this. We're not going to describe this, but there's a paper by Vijay Kumar et al., Task Selection for Multiscalar Processors, that was written in 2001, I believe. You can take a look at that. Basically, there are several things that you need to do. You want to load balance across different processors, right? If one task has 2 instructions, if another task has 2,000 instructions, that doesn't work. So load balancing is important. Again, we go back to the fundamentals. The fundamentals is you would like to minimize overheads, and there minimize the bottlenecks. Remember, the bottlenecks in the parallel portion is load imbalance. We'd like to eliminate that when we're doing task selection. The second is we would like to minimize the synchronization overhead, right? Which means that we'd like to minimize inter-task data dependencies. So the compiler can look at the control flow graphs and figure out the data flow graph also. It tries to minimize the task dependencies. And also it can try to minimize control dependencies, right? Basically, if the control is predictable, if the control transfers between the different tasks are predictable, then this task sequencer can do a good job assigning tasks to different processors and predicting the next task, which is good. If there's a hard to predict branch, it's better to embed it into a task, because if there's a hard to predict branch that affects only this task and nothing else, then you don't need to flush all of the other tasks, right? The branch prediction can be handled solely within this task. So it's good to embed these hard to predict branches within the tasks. And that's one of the jobs of the multiscalar compiler. And you can read the paper for more detail on the benefits of this. The second job of the multiscalar compiler is to convey the task and communication information in the executable to the hardware. For this, the compiler has the task headers, and the task headers specify several things. One is, actually, let me start with the second one. One is the program counters of the potential successor tasks, right? You can have potential multiple successor tasks in a control flow graph. Now, this is the dynamic stream over here, but in a control flow graph, you could actually have many potential successors, and the compiler needs to specify which ones, what are the addresses of those successors, such that the task sequencer can use a prediction mechanism to decide which task to choose next. So let's say this is your task. Now this is your task dependence graph, if you will, or task flow graph. I didn't do this well, but you can imagine there could be many, many successors, right, to a task, and maybe there's an indirect branch, right? So you have these 3 successors after this task, and these successors need to be communicated in the header for this task, such that the task sequencer predicts which one to go to next, which one to sequence to next. The task header also contains information about the register communication, basically which registers are needed by this task, coming from other tasks, because the compiler partitioned the task, right, potentially needed, and which registers are actually created by this task. This is 1 bit per register. The needed registers are actually not here, but created registers are here, but there's a need mask also. Basically, this indicates all registers that are possibly modified or created by the task. These are actual live outs of the task. That's the create mask, right? It's basically one hot bit vector of all of the register that could potentially be modified. There are live outs. And the purpose of this is when you know that you actually are going to modify a task, when you receive, let's say this is your bit vector for the registers that are created, create mask. Let's say this task is modifying register 0, register 5, and register 10. And this task is executing on a processor with this create mask. If another, remember, register file communicates the values. If the register file receives R1, R0 in this case, from the ring, it says, oh, I'm going to create this R0, so I'm not going to use this. Basically, I'm not going to forward this to the next task. Right? So this ensures that the register values are not forwarded unnecessarily. This also ensures that this task actually, when it generates the value, it forwards it to the appropriate places, to other places that need it. Right? There are also release instructions. The compiler also inserts release instructions, which release a register to be forwarded to a receiving task. basically we will talk about release instructions soon. The idea of a release instruction is whenever it's executed, the value it generates is put on this ring. Remember the ring? Let me go quickly to, yeah, there you go. When a processor actually executes an instruction, and it's a release instruction, and it's writing to a register, that register gets put on the ring because it's releasing that register value, or forwarding that register value, and that gets sent to a processor that's later on, and that processor basically captures that value if the value is not already ready in its register file. Basically, if it's waiting for that value. And how does it know it's waiting for that value? The compiler can specify that to the processor. Okay, this is an example multiscalar program. Basically, this is an example code segment over here. What this does is it looks for symbols in a linked list, and if the symbol is not present in the linked list, it adds the symbol. And it does it for a many number of symbols that are specified at this buffer size, right? So this is a hard to parallelize program because what happens is if you break it into iterations, you may get dependencies between different versions, different iterations. So you don't know. It's very hard to analyze statically that there are no dependencies. So multiscalar can actually parallelize this dynamically. And this is the multiscalar code. This is the example. This is the header for the task. This is the task itself. It's basically one loop iteration. You can actually study this on your own. And it has a create mask. These are registers that are potentially created or live outs from this particular task. These are the potential targets. It could be alter, which is the alter loop, which you go back to this same iteration. Or it could be the alter fallout, which means that you actually get out of this iteration. Basically, this is the task itself, and that's you could either get out or you could either continue the loop iteration that does the search for the symbol. Basically, the task does the search for the symbol, and these are the instructions that forward their values. Basically, register 20, register 23. Those are produced with these instructions, and they get forwarded to other tasks because other tasks need them, and this also produces a value. Other tasks need the register 4, and register 8 and register 17 happen to be produced, but they're released with a release instruction, and we will see the reason for release instructions soon. Stop it means basically you stop the task when you reach this instruction. And I'd encourage you to read multiscalar paper to get more details. So how does forwarding registers between tasks happen? Basically, the compiler must identify the last instance of a write of writing to a register within a task. You don't want to. You may be writing to a register many times within a task, but we want to forward the only last value because remember these tasks are from a sequential order. Basically, opcodes that write a register have an additional forward bit indicating this instance when it's executed should immediately forward the result once it's executed to the next processor in sequence, right? And stop bits indicate the end of a task, and release instructions tells the processing element to forward the register value specifically. Basically, you don't you use it. You can either use the forward bits or the release instructions, and there are different cases. Let's take a look at these cases. Let's take a look at this. Let's say this is the task. I'm not showing the control flow instructions here, but let's say you have a load into R1 and another load into R1 over here. Now the second load's value should be forwarded to the next task because next task is really sequential, right? This value is basically consumed within the task, so this value is really dead because it's overwritten over here, regardless of which path you've taken to get to this block. So this load actually is annotated with a forward bit, additional forward bit, indicating that the result of R1 should be forwarded on the ring once this load is executed. In this case, this is a separate case. In this case, the task, depending on the control flow it takes, can produce two different values for R1, right? If the control flow is this way, basically this value of R1 should be forwarded to the next task. If the control flow happens to take go this way, then this value of R1 needs to be forwarded to the next task. In this case, these loads are not marked with the forward bits, but there's an additional release instruction added. Once potential values are produced, then you know which value of R1 is actually needs to be forwarded. Then you can just have a release instruction. The compiler inserts that release instruction such that R1 is just released. And the purpose of the release instruction is basically when the release instruction is executed, that register is sent on the ring to the next processor. That's the idea. And release instruction is needed in this case also, as you can see, because if you go this path, R1 is not overwritten, but an old value of R1 needs to be forwarded. If you go this path, a new value of R1 is produced, and that needs to be forwarded. Okay? So how does task sequencing get achieved? Basically, you have headers contain information about what are the potential successor tasks, and task prediction, the task sequencer, which was here before, needs to do task prediction. And this is analogous to branch prediction, and we've discussed branch prediction in 447. You can take a look at that. The idea is to predict the inter-task control flow. And in this case, for example, tasks are chopped up such that there is only one task following task A. As a result, it's very easy to do this prediction, right? Or in this case, task A has a very iterating loop that iterates many, many times. And task B is the fallout task. In this case, this could be a highly predictable inter-task branch, right? If you look at this. And the prediction may be basically very similar to branch prediction, right? What is the next task coming? In this case, you have two tasks over here, and you predict whether task A or task C comes after task A, and the predictor can get trained, and it can implicitly predict the branches within a task. Right? So that's the idea. This is very similar to branch prediction, but it needs to be done. And an important issue is, how does the compiler form the task such that this prediction is maximized, right? The prediction accuracy is maximized. Okay. How do you handle inter-task dependencies? There are actually control dependencies and data dependencies across the tasks, because the paths actually come from a single sequential stream. Right? For control dependencies, basically we predict, as we discussed. And within a task, there may be dependencies that are control dependencies. Right? And okay, let me go back to inter-task dependencies. If there's a misprediction in the inter-task, subsequent tasks are flushed. Okay? But if there's a misprediction within the task, it's an inter-task misprediction, and I'll show you one example of it. Actually, in the previous example, I could have shown perhaps. Let's say you have this task, and this task starts out this way. And let's say you have an if statement over here and an else statement over here, right? And that's what this is, right? This is the if part, this is the else part, and then you go back. This is a hammock. If there's a misprediction over here, as long as that misprediction doesn't affect anything else, no other task needs to be flushed, right? This misprediction can be handled internally within the task because it doesn't affect the control flow going down. Now, it may affect the data values that are needed by later tasks, but that may be okay. That's dependent, that's handled through a separate mechanism, data dependence mechanism, okay? So basically, intra-task mispredictions are really handled within the task and they don't get exposed. So it's good to embed hard to predict branches into the tasks. That's another job of the compiler that's doing this kind of, that's helping this kind of parallelization. Right? Data dependencies, on the other hand, if data dependencies are through the register file, then we have mask bits and forwarding, as I discussed. Basically, if a task is waiting for a register, then it stalls until that register is available, right? This is a full empty bit synchronization in the register file. On the other hand, for memory, we have a separate store buffer. Multiscalar proposed a separate store buffer called address resolution buffer. And the idea is loads are speculative. Loads speculatively load the values. And if they actually violate it, if they actually loaded a value they shouldn't have loaded, the task is squashed. Let's take a look at this address resolution buffer. Remember, we've discussed there are two fundamental ways of actually storing values, detecting store load dependencies. One is through a separate buffer, and one is through the L1 cache. In this case, we're going to do it through a separate buffer. The idea is multiscalar issues loads to the separate buffer, address resolution buffer, or the data cache at the same time, as soon as the address is computed. Address resolution buffer, ARB, is organized like a cache. It maintains state for all outstanding load and store addresses. And you can read this paper for a detailed discussion. An address resolution buffer entry looks like this. Basically, for each stage, it has it basically takes an address, its address indexed, and for each stage, if you will, stage meaning different processor, it has an entry for that address. And this may not be the best way of doing it, but you get the idea, I think. This is basically a version of that particular location. And this version says, did this stage or did this processor perform a load to this address? And did it perform a store and the data value? And for each stage, you have that speculatively loaded and speculatively stored bits, basically. Right? These are bits that are speculatively loaded and speculatively stored. You could put this into the cache, but they decided to put it in a separate buffer. And this separate buffer actually affects scalability. Basically, when you do a load, let's say you miss in the ARB, address resolution buffer. When any processor does a load, if it misses in the ARB, data comes from the data cache. Because you have not seen any prior stores yet. And if there's an ARB hit, the processor gets the most recent data to the load, which may be from the data cache or nearest prior task with speculative bits set to 1. So if you go back to this, the load can get the data value from the nearest prior task, right? So when you do a load, what happens is the processor checks basically the processor checks all of the previous stages. Let's say stage 2 is doing a load. It basically checks all of the prior logical stages. In this case, let's say head is the stage 0. It checks stage 0 and stage 1 also to see if there's actually a store coming from those stages. If there's a store coming from both stages, then the stage 2 gets its data from here because this is the latest version of the data, if you will. Right? That's the idea. The load gets the latest version from this address resolution buffer, nearest prior task with speculatively stored bit 1. On the other hand, stores, and if the load instruction loads the data later in some way, it sets its load bits as 1 over here, such that if a later task comes and stores, it can detect that violation, right? Okay. Stores, ARB buffers speculative stores. If there's a store from an older task, when it does a store, it basically searches the entry of the ARB, because this is the same block, same cache block. It basically searches to find any later tasks that may potentially have loaded this value, right? So for example, let's say stage 0 does a store to a location. It basically adds the store, adds the data, sets the store bit. It also searches all of the later, logically later locations, stages in this entry to see if anyone has the load bit set, or maybe even the store bit set. Right? If anyone has the load bit set, then that task got the wrong value, so it needs to be squashed. That's the idea. Basically, it's a store to load forwarding mechanism, and also misspeculation checking mechanism. This is how you detect the misspeculation. And when a task commits, all of the task stores are committed into the data cache from the address resolution buffer. Right? So basically, this is very similar to the speculatively loaded and speculatively modified bits that we saw earlier with thread level speculation, right? Because it's essentially the same concept, except we're doing this not in the cache, not using the coherence protocol, but we're doing this with a separate data structure called the address resolution buffer. Okay, and if you'd like to learn more about the address resolution buffer, you can take a look at this paper. This is actually introduced a bank design for different processors, and you have 6 processors in this case that can be part of the design. But this is actually a centralized structure that is not that scalable. It may be easier to actually use the coherence protocol, some coherence mechanism to forward data values between different processors through memory, and also detect violations, memory dependence violations. Okay, so this was memory dependence violation detection, right? It's actually memory renaming, right? You have you have different versions of the same cache block with the same tag in different stages of this ARB entry, as we've seen, right? Basically, what ARB does is really memory renaming, right? The same location can have multiple different values, right? Except they have different versions depending on which task actually modified or executed them. But what it does not do is memory dependence prediction. Maybe you want to be more aggressive, because once you violate the dependence, you need to squash the task. It's already too late. You've already used the value. But can we predict that early on, right? You can actually reduce this intra-task flushes flushes or squashes due to inter-task dependency violations by doing accurate memory dependence prediction. And we'll cover that next. The idea is predict, when you're doing a load instruction at task, predict whether or not a load instruction will be dependent on a previous store, and predict which store it is. And delay the execution of the load if it's predicted to be dependent on a previous store. And if you can do this accurately, then you reduce the amount of squashing that happens between the tasks. And existing processors actually do this within the instruction window, because within the instruction window, the problem is similar, right? You may have a store, older store, that's writing to a location that a younger load is writing, but when the load executes, it doesn't know it. That store has not even executed yet. So that's the idea. And there are two seminal papers that I would recommend. One is Andreas Moshowos' Dynamic Speculation and Synchronization of Data Dependencies that appeared in ISCA 1997. That's within the context of multiscalar processors. And the other is Christos Zemmer's Memory Dependence Prediction Using Store Sets that appeared in ISCA 1998. But let's briefly talk about handling of these store load dependencies, because this is actually important in an out-of-order execution processor too. Because in an out-of-order execution processor, you have the same problem. The problem is a load's dependence status is not known until all previous store addresses are available, right? And there are two key questions. One is, how does the processor detect dependence of a load instruction on a previous store? The second, how does the processor engine treat the scheduling of a load instruction with respect to previous stores? So that engine should not be here in the slides. How does the processor treat the scheduling of a load instruction with respect to previous stores? So let's take a look at the first question. How do you actually detect the dependence of a load instruction? Well, one option is to wait until all previous stores are committed, are done, computed their addresses, right? Then there's no need to check. This is the memory disambiguation problem. The second option is keep a list of pending stores in a store buffer and check whether a load address actually matches a previous store address. This is the load store queue that we've discussed earlier in the multi-core lecture. And if you've actually taken my class 447 in its out-of-order execution lecture discusses also the store queue, right? Basically, keep a list of pending stores. How do you actually treat the scheduling of a load instruction with respect to previous stores? Basically, when you get a load instruction, when do you schedule it? There are three options depending on different aggressiveness levels. The first is you can assume that the load is independent of all previous stores and schedule the load right away. This is what we were doing earlier, right, with a lot of the thread level speculation approaches that I've discussed. The second is you can assume load is dependent on previous stores. So the first one is the aggressive approach. The second one is the most conservative approach, which is you can assume load is dependent on all previous stores and wait until all previous stores and all tasks have completed. This is very bad because this reduces your parallelism significantly, especially if you're designing a very large instruction window. The third option, which may be more intelligent, is to predict the dependence of a load on an outstanding store, right? Basically, this is the idea of the memory dependence prediction. So let's take a look at these three options. Assuming load is independent of all previous stores, the advantage is simple and can be the common case, right? There may not be many stores that are producing values to nearby loads. So there is no delay for independent loads in this case, right? And previous research has shown that most loads are actually independent. The downside of this is it requires recovery and re-execution of load and depends on misprediction. And when the misprediction rate increases, the performance tanks in this case. The second option is to assume the load is dependent on all previous stores. There's no need for recovery in this case because you're really waiting conservatively until all previous stores have been resolved. And that's the downside. It delays independent loads unnecessarily. So this performs badly also. Third option is more intelligent perhaps. Predict the dependence of a load on an outstanding store. This is more accurate, because it turns out load store dependencies persist over time across tasks also. So if you actually have a single instruction window divided into these tasks, let's say task 0 and task 4, it may be that this is doing a store and this doing a load, and this static store and this static load always are to the same address. Now if you can figure this out, this is a great prediction. If they're always to the same address, you know that when this task executes this load, if this store has not executed yet, you'd better wait for that store, right? And that's the idea that's proposed by these two papers, Moshowos and Christos and Emmer. I'll refer you to those papers. I'm not going to talk about them in detail, but the mechanisms are basically built upon this idea. And why would this happen? Well, think about, for example, stack-based communication. It may be that you're storing a value onto the stack, and you're doing a function call, and you're doing a loads for that value from the stack, right? Because you don't have enough registers, for example, right? You're spilling the value into memory from a register. because you don't have enough registers, and this load is later loading or filling the value because you've spilled it earlier to memory. In this case, this is a very predictable dependence, right? So that whenever this load executes, you know that somebody else spilled it. Well, unless there are other writes to that location, but with spills and fills, there are usually no writes. So this is one of the reasons why memory dependencies persist between loads and stores. Okay, so the upside of this is it's more accurate, right? The downside is it still requires recovery and re-execution on misprediction, right? In fact, Alpha 21264, this is one of the readings that I recommended to you. Rick Kessler's the Alpha 21264 microprocessor paper that appeared in IEEE Micro in 1997. And if you have not read this, I would strongly recommend that you read it. The Alpha 21264 microprocessor that talks about a lot of the ideas that are introduced and implemented in the Alpha 21264, which was one of the fastest processors of its time. Basically, Alpha 21264, when it executed a load instruction, it first assumed that that load is independent of any store, so it went ahead and executed it. And later, of course, there's a mechanism to verify if that execution was correct, because it had load store buffers, as I discussed earlier, right? Whenever a store executed, it basically checked the load buffer and tried to find instructions that shouldn't have been executed. Tried to find instructions that are that have a larger sequence number than this than itself, and also that has an overlapping address. And the store detects that violation, and once there's a violation, the load shouldn't have been executed, and this loads that are found to be dependent are delayed. Basically, the load instruction is marked with a separate bit in the instruction cache saying that this load should wait for all of the previous stores to finish. So this was a hard measure, basically saying that you should wait for all of the previous stores in the machine to compute their addresses. It didn't associate the load with a particular store. It associated the load with all of the stores in the machine. But that's the Alpha 21264 did this memory dependence prediction, and that memory dependence prediction mechanism was actually quite effective in terms of reducing the, in terms of handling, basically quite effective compared to both option 1, which is aggressive, and option 2, which is conservative. And this is one example from Christos and Emmer paper. It shows basically the IPC on the y-axis and different benchmarks on the x-axis. It shows the conservative approach, which is no speculation. And if you see that the conservative approach is quite bad in most cases, the IPC is low. Actually, it's the lowest in most cases. It also shows the aggressive approach, which is the naive speculation. Basically, all load instructions are assumed to be independent of previous stores. And this is actually better in most cases compared to conservative approach, because you're actually, this points to the fact that many loads are actually independent of the store, so you'd better let them go. And this last one shows the potential of perfect prediction. You basically perfectly figure out if the load is actually dependent on a previous store with an oracle mechanism and simulate this, and wait only for that store to be executed to execute this load. And that actually provides the highest performance. So there's actually significant potential with perfect prediction compared to naive and both conservative and aggressive speculation mechanisms. Well, conservative handling and aggressive handling mechanisms. No speculation means basically the load waits until all of the previous store addresses are available. So this shows that predicting store load dependencies are important for performance. And actually simple predictors like what they propose in this paper or the Alpha 21264 predictor can achieve most of the potential performance. And I'll encourage you to read the paper as well as the Alpha 21264 paper to see the different predictors. And Christos and MM paper provides a good analysis of their predictors and other predictors. Okay, now we're done with multiscalar. I'd encourage you to do some comparisons of multiscalar. Basically, how does this compare to superscalar out-of-order processors? There's some comparison with a single instruction window that we've discussed, right? How does it compare to multi-core processors? This looks kind of like multi-core, right? Except we're speculatively parallelizing things. And except there's this weird thing going on with the register file, which is the round-robin communication, interconnection network that's tightly coupled to the register file. How does this compare to other chip multiprocessor and SMT, simultaneous multithreading based thread level speculation mechanism, like thread level speculation that we've discussed earlier, right? The Steffan paper. So what is different in multiscalar hardware than in these approaches, and what is different in multiscalar software? I'm not going to go through this in detail, But one thing that I'll question is the scalability of fine-grained register communication. For example, the Colohan paper looks at does communication between different tasks through the coherence protocol that already exists. And there is no the register-based communication is not there, right? Whereas with multiscalar, there is a register-based communication component, and this is very fine-grained, and this adds another point in the register file. This ring stop that goes into the register file adds another port into the register file, right? Now you need to synchronize accesses, arbitrate between accesses that's coming from the local processor as well as the ring that's going to the register file. So how does it scale to many processors? And this may be one of the Achilles heels of multiscalar implementation. This register file, very fine-grained register file communication may be difficult to implement in hardware because register file is a very important component that's on the critical path of the local processor. Now if you add one more port to it, maybe it becomes more difficult to design, and also you need to somehow do arbitration between requests coming from the local port as well as the side ports. The second issue of scalability is the scalability of memory renaming and dependence speculation. How can you scale this? And this is usually a big problem with thread level speculation approaches. How can you actually make the memory dependence detection and violation detection mechanisms more scalable? With use of the coherence protocol, perhaps you can do that, but you can be as scalable as the coherence protocol, right? In multiscalar, the address resolution buffer is a centralized structure that's much less scalable than a directory-based coherence protocol, for example. So this is something to think about also. This is food for thought for you. Okay, let's move on to another speculative parallelization mechanism, which is helper threading for prefetching. And we've looked at this idea in 447 actually, but the basic idea is to pre-execute a piece of the program solely for prefetching data. Before, we were not solely for prefetching data. The multiscalar actually chops up the program and tries to merge the results in the end, right? Whereas here, we're going to use this additional context to purely prefetch data. And in this case, you only need to form a smaller version of the program that leads to cache misses to be able to capture the most of the benefit. Basically, speculative thread, this is the pre-executed program piece can be considered a thread. It actually can be launched as a thread. And this can be executed on a separate processor or core, on a separate hardware thread context, or on the same hardware thread context in idle cycles during cache misses, right? This is, remember, run-ahead execution does this, right? When you get a cache miss, you keep executing the speculative thread to actually, you keep executing the program to actually generate prefetches in a speculative way. Okay, so this shows the generalized thread-based execution here, and these are some of the papers that I would strongly recommend for you to read. Basically, what we have, let's take a look at load in this case, but you can actually generalize this to any instruction that leads to some performance degradation. Let's say we have this load, and this is our main program. The idea is, while you're executing the main program, you also launch a thread, fork a thread, that executes a prune part of the program that is concerned with generating the address of this load, and that executes while the main thread executes, and that leads to a cache miss. And by the time this load actually executes in the main thread, a lot of the instructions are redundantly executed in the main thread, this load hits in the cache because this speculative thread already loaded the value into the cache. And as a result, you get some speed up, right? Now this load is not a miss anymore. That's the idea. And this idea is actually described in many different papers, and these papers are examples. Assisted execution is one example, for example. And you could do this for branch mispredictions also. Let's say you have a hard-to-predict branch. You can start a thread, you can speculatively launch a thread that executes the dependent instructions that lead to the outcome of the branch and produce a prediction. And once the branch is being fetched, you can read this prediction from a prediction buffer, right? And that's how you can predict the branch. And these papers concern themselves, Chappelle et al., simultaneous subordinate microthreading, Zils and Soy, execution-based prediction using speculative slices that talk about some of these branch prediction issues also. So that's the generalized. With the generalized thread-based pre-execution, there are three key questions. Where do you execute this pre-computation thread? Basically, you can think of this thread that's generating results, prefetches, and branch prediction outcomes as pre-computation thread, right? Where do you execute this? when do you spawn this pre-computation thread? When do you terminate the pre-computation thread? These are key issues. I'm not going to go into these in detail, but we'll talk about several options. You can execute the pre-computation thread on a separate core. This leads to the least contention with the main thread, right? Because the main thread is executing the main program, and pre-computation thread is executing the pruned version of the program that will hopefully generate cache misses, right? Or that will hopefully generate branch mispredictions. And basically, you have core 1, core 0, and core 1. You can execute the main thread here, and you can execute the speculative thread here. There's no contention between speculative and main thread in this case, which is good. But the downside is they're not communicating tightly together. They're communicating through the shared L2, for example. So communication may be hard to do this, and they are private L1s, right? You can do it on a separate thread context on the same core. You can have the main thread, you can have two thread contexts here, main thread and speculative thread executing here, right? In this case, there's more contention, so they can delay each other, these different threads, but the upside is they can more tightly communicate through the L1 cache, right? The prefetch is going to the L1 cache, right? You can also do it on the same core and the same context. Basically, I'm going to remove this, but you have the same core executing the main thread and also the speculative thread. And in this case, when the main thread is stalled, you can execute the speculative thread. So there is some contention in this case, but it may be okay if you're actually executing the speculative thread in the same when the main thread is stalled. The second issue is when do you spawn to pre-computation thread? Basically, you have a load instruction here, and where do you find the fork point? When do you spawn? If you spawn too late, maybe prefetch the thread that's executed reaches this load later than the main thread would reach, right? Or maybe it doesn't overlap the latency of the cache miss because main thread is going to reach that load anyway very soon. If you spawn too early, let's say you fork over here, and this thread, the speculative thread, reaches the load and gets a cache miss and handles the cache miss, but this main thread may never reach this load because you spawn too early. There's a bunch of branches over here, and this thread actually will never reach the same load because the branches are taken some other way, right? So too early is maybe bad also. And too early also can have other downsides. For example, this load may pollute the cache. This load may be kicked out before it's needed, or it may kick out some useful value that's needed over here, right? So it can cause cache pollution. Or you can spawn the pre-computation thread. Basically, there are trade-offs associated with them. These trade-offs are important to do, whether you're generating the threads in the compiler level, at the programmer level, or at the hardware level, right? Or you can do it when the main thread is stalled, right? You can spawn the pre-computation thread when the main thread is stalled, and people have looked at that also. One interesting paper about this is virtual multithreading, and you can read that. I believe it's in ASPLOS 2004. This basically talks about the experiences of when a main thread is stalled, launching the prefetch thread on the same core in an Itanium processor. And of course, run-ahead execution, when the main thread is stalled, run-ahead execution kind of launches a speculative version of the same program, right? And then by checkpointing, you're actually generating a new thread, if you will, that is of the same program. The third question is when do you terminate the pre-computation thread? Basically, you can do this with pre-inserted cancel instructions, or if the thread is not being effective anymore, you can terminate it, right? Maybe the main thread actually reached the point that the speculative thread is actually trying to prefetch for, right? It's too late at that point, so the main thread can say cancel. There can be a cancel instruction that actually cancels the speculative thread at that point. Or the runtime system can dynamically collect effectiveness and contention information about the threads, and based on that information, it can decide to kill the pre-computation thread. So there are a bunch of thread-based pre-execution issues that we're not going to be able to cover, but this is a fascinating topic also. And if you want to do research in this area, this is I would strongly recommend this paper by C.K. Luke, who on tolerating memory latency through software-controlled pre-execution and simultaneous multi-threading processors. Basically, it discusses many issues in software-based pre-execution, and the goal of this paper is to actually generate prefetching threads for hard-to-predict data structures. For example, if you look at this here, the main execution can be going through a pointer chain, and pre-execution can be going through the other pointer chains. For example, if this is a hash table and you have many hash lookups, when the main processor, the main execution, main thread is doing a hash lookup on one key, the other processors can be pre-executing threads that are doing hash lookups on the future keys that may come up, right? And there are a bunch of other ones. Here, for example, multiple procedure calls. You can do function-based parallelization. When the main processor is executing one function, the pre-execution can be executing different functions. This way you can achieve function-level parallelization. And this paper talks about many issues, and I'm not going to go over this example, but this is basically an example that shows, this is actually from MCF. It's a memory-intensive workload from the Spec 2000 and 2006 workload suites. And this is an interesting workload. Basically, what's happening here is you have a loop, while loop here that traverses. This is a vehicle scheduling program, by the way. You're basically trying to schedule vehicles to service customers. And what's happening is there's a linked list traversal over here. And for the different trips, you do many linked list traversals to find the right vehicle. And while you're doing this linked list traversal, the idea is to do pre-execution for the next linked list traversal, right? When you're doing the execution for this iteration, why don't you start the execution for the next iteration? So that's what this pre-execute start instruction does. It starts the pre-execution of this part as a next iteration. And the next iteration basically executes the next traversal for the next trip over here, right? And there's a pre-execute stop over here. And there's that basically ends the pre-execution for that next iteration. And there's this pre-execute start actually starts. So this is the main thread. When you're executing the main thread, this is actually all of the threads. When the main thread is executing, when it gets to this point, there's a pre-execute start that starts from end 4, which starts from the next iteration, right? It sets up the next iteration and starts the next iteration in some other context. And the main thread keeps executing this iteration, and the pre-execution thread now keeps executing the next iteration, right? It also gets the pre-execute start. Now the question is, do you do nested pre-execute starts? In this paper, I believe they did not do it. But you could do nested pre-execute starts, right? The pre-execution thread can launch another thread. That's another pre-execution thread. Okay, so the pre-execution thread stops when it finishes the next iteration, right? And the pre-execution thread can also stop over here. If there is no next iteration left, there's another pre-execute stop over here. So this is how you can actually parallelize a program with pre-execution thread. And there needs to be some ISA extensions over here. For example, pre-execute start takes the start PC and some maximum number of instructions to execute potentially, and generates a thread ID. Pre-execute stop, the thread that's doing the pre-execution can be self-terminated, right? And pre-execute cancels mean the main thread, for example, when it does pre-execute start, it records the thread ID and can decide to cancel that thread later on. And there could be many reasons why to cancel this thread, and the paper talks about some of them. So this paper actually shows some promising results also. These are results from different applications with an SMT, real SMT, simultaneous multi-threading processor at that time. And basically, if you look at this is the execution time normalized without pre-execution, and execution time normalized with pre-execution. So with pre-execution, you get significant performance benefits on some of these applications. So MCF gains 8%, for example, with 2 contexts. MST, the minimum spanning tree computation, gains about 36%. Ray tracing program gains 23%. Some programs actually lose performance because pre-execution consumes bandwidth and leads to contention, and there's a 5% degradation in compressed, for example. And the paper is a very interesting paper to read, so I would strongly recommend you to read it. There are a couple of other papers that actually discuss how to construct these backward slices, the threads, the pre-execution threads, and these Zillis and Soy papers are interesting reads over here. This is another example from one other Spec 2000 program, which is VPR, Virtual Praise and Route. The basic idea, this is one of the loops over here, and turns out this is a costly branch because it has lots of branch misdirections, and this is a costly cache miss. Let's take a look at how you actually construct. I'll just give you an example. I'll refer you to the papers for more details. But this paper talks about where you actually can insert the fork point to actually prefetch for this particular program, and you'd like to insert the fork point earlier, much earlier than this particular function before it's called in this case. And these are some of the instructions. Basically, the key question is when you actually try to generate a thread just to prefetch data or just to compute a branch outcome, do you need all of the instructions? If you needed all of the instructions between this point, this fork point, and the load, then having a pre-execution thread doesn't make sense, right? Because the main thread is going to execute all of those instructions anyway, right? Usually, actually, it may make sense if the speculative thread actually skips those instructions somehow, right? But in this case, we can actually reduce the program because not all instructions that happen between the fork point and the problem instruction actually lead to something useful to compute the address of the problem instruction or the outcome of the problem instruction, right? And this shows an example over here. There are many instructions between the fork point and the problem instructions, but you only need this many instructions. And you can count these: 1, 2, 3, 4, 5, 6, 7 instructions, or maybe 8 instructions execute in the pre-execution thread to actually capture to actually compute what's needed to compute for these problem instructions. So you can prune the program significantly just to focus on these problem instructions. As a result, this pre-execution thread can be much leaner than the main thread, and it can execute quickly. Right. Now we will see that there could be other methods of constructing this pre-execution thread, right? You could actually skip some instructions. You could actually value predict some instructions such that if you don't know the values, input values to the thread, you can predict the values coming into the thread. Because this is purely speculative, right? The goal of this thread is to improve the performance of the main thread. That's what you can achieve with purely speculative approaches. Run-ahead execution is an example of this approach also. Remember, this is a pre-execution method for prefetching purposes, and we've discussed this in an earlier lecture, and there's a spring 2013 video that talks about run-ahead execution. This was my PhD thesis, and other people have worked on the problem. Dundas and Mudge looked at it in-order processors in ICS 1997. But basically the key idea is when the oldest instruction is a long latency cache miss, the processor checkpoints the architectural state and enters a speculative processing mode. You could now consider this a speculative thread because its state is checkpointed. In run-ahead mode, instructions are speculatively pre-executed, and the purpose of pre-execution is just to generate prefetches, just like this helper thread. So run-ahead execution really generates a helper thread, uses the main thread as the helper thread. And the L2 misdependent instructions are marked invalid and dropped such that space can be made in the instruction window for other instructions that are independent. And the hope is that while this thread is executing, it executes some independent instructions, and it gets to some cache misses that wouldn't have otherwise been uncovered with the instruction window that you have. And these cache misses are prefetched, and run-ahead mode ends when the original miss returns. At that point, checkpoint is restored, and main thread starts re-execution from the beginning, from the point where the speculative thread actually continued execution to begin with. So normal execution resumes. Basically, what happened was instead of stalling for this load, you switched in this run-ahead thread, if you will, that executed quickly and got out of the and actually prefetched for the main thread. So let me give you this example, and I'll take a quick break right after that. Basically, with a small window, this is what happens. The processor computes, and it gets a cache miss, and normally it stalls, right? And later, it gets another cache miss and stalls again. With run-ahead execution, the processor gets a cache miss, and it enters this run-ahead execution mode where it speculatively processes the instructions. You could consider this a speculative thread. And while the speculative thread is executing, it gets another load miss. And if this is independent, it can start servicing that load miss. And this miss starts being serviced in parallel with the original miss. Run-ahead execution ends when this first miss comes back from memory. The processor's pipeline is flushed. And now the main thread, if you will, starts executing because the checkpoint is restored, and the processor starts from the program counter of the load 1. Now load 1 hits because the miss is serviced, and the processor main thread continues execution. After that, at some point, the second miss gets complete, and when this load 2 actually executes, what happens is it hits in the cache, right? Because the speculative thread that got executed during the stall cycles actually prefetched data for the main thread that gets executed in the non-stall cycles, if you will. So as a result, you save significant amount of time with run-ahead execution. So run-ahead execution is another example of speculative parallelization of the program, just like a helper thread, except run-ahead execution uses the main program. It doesn't really prune the program. It just uses the main program to actually generate cache misses. Now going forward, there are actually interesting research issues here, and I'd be happy to talk to you about it. How do you actually make this run-ahead execution to be more effective? Can you actually prune this program dynamically in this run-ahead mode to actually improve the performance and efficiency of run-ahead execution? And that's a very interesting topic going forward. So I'll take a break here. We'll start with slipstream processors at the beginning of the next video.